Today our lab is the force table lab, or one of our labs is the force table lab. And if you're doing that this week, then we need to talk a little bit about it. We'll show you a little bit later a picture of the apparatus and how to operate it in detail, but let's talk a little bit about the theory. Okay, so the theory is Newton's first law of motion. That is, the sum of the forces is zero. This sigma stands for sum, and of course the arrow on top is an indication of a vector. And again, one thing you need to do is before you do anything, before you do a homework problem, before you work on a lab, you need to see that you're working with scalars or you're working with vectors. Those are important distinctions. If you work with scalars, which you've done in high school and grade school, just numbers, manipulating numbers around, that's fine. But if you have vectors, then as you probably already know, we have components, and the mathematics involving vectors is a little bit more tricky. So we have vectors. That's the purpose of this lab, really. It's a vector addition lab. That's what it is. It doesn't seem like it when you draw vectors on your piece of paper or on the board, little arrows in different directions. You'll see that that's sort of easy to understand, but when you look at the force table in front of you, a nice three-dimensional force table, it all of a sudden gets confusing, which it shouldn't, because it's just vector addition. So when you do this experiment, I recommend that you sketch a little picture of the table, which is a round table, and I would set it up so this is like the plus x-axis at 0 degrees, this is 90 degrees, and this is 180 degrees, the minus x-axis, and this is 270, the minus y-axis. So it's set up like a coordinate system. And then you can superpose on top of that the drawings of your actual forces that you're going to be dealing with that you've measured in the lab. Again, forces are forces and not masses. In order to get the force that we're dealing with in this experiment is the force of gravity, and of course Newton's second law, which involves accelerations, which we're not dealing with here, except we are dealing with the acceleration due to gravity, which is straight down, and if you multiply the mass of whatever it is you're working with times the acceleration of gravity, you have a downward force. And the purpose of this table is to change the downward forces to horizontal forces, so you can look down on the table and see this force goes this way, that force goes that way, and it looks like this, and you can draw that nice picture of it. So force of gravity is the mass times the acceleration due to gravity. Please keep in mind little g stands for the acceleration due to gravity, not gravity. So it's an acceleration. So we will at some point have to multiply these masses in kilograms by 9.8 meters per second squared to turn them into newtons. And we should work with newtons. So we have to do that conversion, divide by 1,000 to change it into kilograms from grams, and multiply by 9.8 meters per second squared to change it into newtons. Okay, so back to our first law of motion here. The sum of the forces adds up to 0. That means it's in equilibrium. That means that it is not either not moving, in which the forces add up to 0, or it's not accelerating. It has a constant velocity. That's kinetic equilibrium. We have static equilibrium here, so the sum of the forces adds up to 0, and nothing's moving. Okay, so we take these, let's just take this, again, here's your sketch, and we're going to start out in part 1 with forces at 0 degrees, 90 degrees, and 240 degrees. So this is 0 degrees, this is 90 degrees, this is 240 degrees. So we have force 1, force 2, and force 3. Okay, these vector forces add up to 0, which means, and that's the thing about vectors, the first thing you do as soon as you can, you break them into component equations, which are scalar equations, which you're familiar with from high school and grade school. So this is broken up into an x equation and a y equation, x and y being horizontal components. So we have the sum of the forces in the x direction is 0, and the sum of the forces in the y direction is 0. These are scalar equations, which are much more simple to work with, and we're going to see how this works out. So we want to write these two equations. What this really means, let me expand that. That means that the force, the x component of the first force plus the x component of the second force plus the x component of the third force have to add up to 0. And this means the same thing for the y components. So we're looking at the x component, sum of the forces in the x direction is 0. And again, f1x plus f2x plus f3x has to add up to 0. Again, as I said a minute ago, there is no x component for force 2. It's straight up. It's got a y component only. So that's out of the picture here. F1x plus f3x is 0. We don't want to compare to 0, so we put f1x equals minus f3x. So we can compare something on this side to this side, neither of which is 0, and get a good percent difference. And similarly, we do this for the y component equation. And if you look at the y component equation, F1 is a force only in the x direction, so it doesn't have a y component. So we have F2y, and again, if we put the F3 component on the other side, we have minus F3 equals minus F3y. So we're going to check out to see if this theoretical value and this experimental value are the same. They're not going to be, because this is physics, it's an experiment, and nothing is perfectly measured, so we're going to do that. So we need to get some data to do that. Let's just make up some data for kicks here. Let's say that f1x should be 56 grams times 1/1000, 1,000 grams, 1 kilogram times 9.8 meters per second squared, and that's going to give something like 0.055 newtons, roughly. I'm just making that rough calculations, but I think that's pretty close to right. So we want to compare that to what we actually get on the balance. So we can calculate what it should be, and let's say we get 0.057 newtons on the balance. If we just take the weights off, don't forget to add the 5 grams for the pan, and convert that, and we'll see. So this is the actual answer that you get by weighing it. This is the experimental answer, or not by weighing it, by counting up the weights on the pan and adding 5 grams for the pan. So we have a discrepancy, which is not unusual, and we want to figure out what's the percent difference. So our true value, actual value, accepted value, whatever you want to say, is 0.57, and so our experimental value is 0.55 minus 0.57 divided by 0.57, and this is 0.002 divided by 0.057. This is 0.035 times 100, change it into percent, which is 3.5. We'll call it 4%. So these two x components are off by 4%. I think you're going to come out better than this, but this is just an example. And you can do the same thing for the y components. Again, we're comparing a non-zero value to the expected non-zero value. So that's part one. And all it hopes to show you is that, yes, indeed, the vector sum of the forces is indeed to within experimental error zero. We'll talk about experimental error a little bit later when we talk about the apparatus, but that's where you have to come up with a decent estimate for experimental error. That's the part that you probably haven't done too much of in high school. You've just gotten the answer and said, well, they're off by 4%, whatever. Usually we round the percentages, as you know from our talk a couple weeks ago, to one significant figure. Okay, so part two, we have unknowns that are little rectangular, crudely cut out chunks of aluminum with a hole in the middle so you can put them on the weight holder pan. Part two is both one unknown. So, and with part two also, I want you to use different angles. We don't want our x components and our y components and a couple of these forces to be zero. We want them to have some number, because you need to get used to working with components and adding like components to get an answer, which is what we're all about. So in part two, put your angles at any old place except like 120 degrees apart. That's not fair, because you know that the forces are all going to be the same. And you don't want them at 0 and 90 and at 270 and at 180. So we're going to pick, say, 20 degrees, 120 degrees, and 250 degrees. Something like that. F1, F2, F3. So procedure is the same. The sum of the forces in the x direction adds up to 0, and the sum of the forces in the y direction add up to 0. We don't have to do any funny business here, because that is by moving one over on the other side and making it minus. We've done that. We've shown that the vector sum of the forces, we hope, within our experimental error, is indeed 0 for part one. Now we want to use that fact for part two and part three. So we have a noun. Let's see this is, call this one F1, and we'll call this F2, and we call this, we can call this F3, which is the unknown one now. Okay, so we're going to know what's on these pans. We're going to have something on this pan. It's going to consist of the unknown, which is somewhere around 20 grams, just a helpful hint, plus the 5 grams for the pan, plus whatever extra weights you have to add to this to get it balanced, and we'll talk about the balance in a little bit. Okay, so here's my diagram, and of course we still have the sum of the forces in the x direction equals 0, and the sum of the forces in the y direction equals 0. And so let's do those. I mean, if you want to write these again, they're the same as last time, except the angles and the forces are going to be different. I don't like two equal signs in the expression, so F1y plus F2y plus F3y equals 0. These are independent equations. I think you've seen, or you will see shortly in class, when you have independent equations, pretty obviously something in the y direction doesn't have an x component. Something in the x direction doesn't have a y component. And so they are independent of each other. These components are independent of each other. So we have two independent equations here, and they both have, we might say, well, they both have an unknown in each one of them, but you don't want to go there because you know this angle is 250 degrees. So before you put some numbers in, you want to rewrite that again as F3 times again, this is the cosine of 250 degrees, and the y component is F3 times the sine of 250 degrees. So we have these unknown components written in terms of not totally unknown, but the angle is known, so we're going to put that number in there, and the forces, the force F3. So we get two calculations for the same thing. F3, the total force on the pan number 3. So calculate these each way, with each component, and average the answers for your F3, not F3x and F3y, but for F3. And find the percent difference, and hopefully that will be within your experimental error range. And so that's part 2. So the procedure in part 3 starts out to be the same as the procedure in part 2. In fact, you can use the same angles in part 3 as you used in part 2 if you wish. But here the difference is, again, let me draw my little sample here. Let's see, that's F1 is at 20 degrees. F2 is at 120 degrees. And F3 is at 250 degrees. Okay, so again, the components are the same. You write out the same component equations, F1x plus F2x plus F3x equals 0, because you've shown in the first part that, yes, within your experimental error, they do equal 0, and Newton's first law works, thank heaven. So we're going to do it this way, and we have the same equations, F1x plus F2x plus F3x is equal to 0, and none of these are 0 because none of these are along one of the component axis, the xy axis direction. F1y plus F2y plus F3y equals 0. So same procedure. We've shown it 0 in part 1 to our satisfaction, we hope, and that we have verified Newton's second law in the first part. But these two, now we'll say the two unknowns, we can make them up as either any two you want. Let's say F1 and F2 are the unknowns. But again, they're not totally unknown because we know this angle is 20 degrees and this angle is 120 degrees. So we can rewrite this expression as F1 times the cosine, that's the x component, again, right here's F1, this is F1y, this is F1x, this is 20 degrees, is that right? Okay, 20 degrees, and so F1x is F1 cosine of 20 degrees, F2x is F2 cosine 120 degrees, and we don't know what F3x is, but we do know that it's at 250 degrees, so it's F3 times the cosine of 250 degrees. That has to add up to 0, right? So we know all these angles, they're sines or cosines, depending on the x and y components and how you measure the angle. And so we can put all the numbers in here. This number we know, it's the known number this time, and we know this, in other words, this is a number that's totally known. And this is known, and this is known. And so I'll have this F1 times some number plus F2 times some number plus a number. And same thing in the y direction, F1 y cosine, or sine, of 20 degrees plus F2y times the sine of 120 degrees plus F3, those are not, F3y times the sine of 250 degrees equals 0. Again, you know this, you know this, you know this, and you know this. So all you don't know are these numbers here. And oh, by the way, I shouldn't have done this. This is F1, not F1y. This is F2, not F2. These are F1 and F2 because the y component, this is the y component of F1. So we have F1 and F2 in two equations with two unknowns. That's the tricky part. You have to solve those simultaneously, and you might need some helpful hints from your instructor, or think back to high school days where you had to solve two equations with two unknowns simultaneously. So that's what you got to do here. So you only get one shot at each value for the unknowns. And yes, one of these is the unknown you used in part 2, but play dumb and pretend you don't know what it is. Don't use the number from part 2 in part 3. it's all of a sudden magically become an unknown again. And then see how those come out, and see how the value for the one unknown that you did know in part 2 comes out compared to the unknown that you calculated in part 3. Okay, that's it. That's the procedure. Well, here's the force table that we put on the floor, so you can take a look at the pans and the weights on the pans, and it's relatively balanced. Okay, so if you look straight down, and you have to look straight down, you'll see that there is a sort of a bullseye in the middle. First of all, you need to make sure that these strings are lined up, attached to this ring, and at roughly the same angles they are here. Like this is a 90-degree angle. These strings are 90 degrees apart. This is a bigger angle, so the strings it's not over here, it's over here. So you need to adjust the strings so that they have the same geometry as these 3 pulleys do, and then it'll be more accurate. So now if you look straight down on it, which we're doing, you see that it's almost balanced. And it turns out, if you play around with this for a while, with the smallest weights that I suggest using, which are 1 grams, not ½ grams, you'll be tearing your hair out trying to balance it to the nearest ½ gram. So we'll go for 1 gram. So let's say we have one of these pans has 100 grams on it. And so it looks to be as balanced as it's going to get, and you'll have to become the expert at that by seeing how close to centered you can get it by continuing to put a little bit extra weight around here and there, and getting it to balance the best you can. So let's say we've done that, you've done that, and so we need to see how sensitive this apparatus is. That's an experimental error. So I'm going to put 1 gram on the pan that has the most mass, and it should stop wobbling here just a minute. Okay, and you see that's clearly knocked off balance. Okay, so 1 gram out of 100 grams, I'm not converting it to newtons right now just for the sake of percentages, the 1 gram out of 100 grams total is 1%. Okay, so I've added 1% more mass to this, and it clearly knocks it off balance. It's way off balance, in fact. So what that means is this entire apparatus, because all 3 pulleys and platform, all 3 pulleys moved, that the entire force table is knocked off balance by about a 1% addition or to one of these pans, preferably the one with the most mass, because 1%, 1 gram out of 100 is 1%, 1 gram out of 50 is 2%. So you want to put it on the mass that's already the biggest to get the most accurate deflection. So 1%. So the entire apparatus has, because of the pulleys and so forth, about a 1% error. Now, when you do this experiment, I mentioned in the write-up that you should rap with your knuckles very lightly, as I did there, to shake everything just a little bit, because you'll learn shortly that the coefficient of static friction is greater than the coefficient of moving friction. So if you get things moving, there's a little less friction. And I think you know that from everyday experience. So when you get it balanced, tap it, and when you want to add this extra mass, also tap it to make sure that the pulleys are free to move around, and it does go off balance. So the apparatus has 1% error. And just because we need to give you some hints on how to do this error analysis business, again, we have 3 pans, and I've not asked you to take the masses off the pans and put them on a double pan balance and mass them accurately to the nearest 100th of a gram. I'm just going to say, and that's typically the case in the lab, that all the masses, all the weights we're going to use are accurate to 1% or better, so 1% at the worst. So we have 3 pans, and we have 3%, possible 3% total mass error in these 3 pans, plus a 1% from my calculation, for the sensitivity of the apparatus, that's 4%. So what I'm saying is that you should look back at your results and see that they are each within 4% of the correct answer. And you get the correct answer, of course, for the unknowns by actually finding their mass on the double pan balance. So you have a reference there which is accurate to the nearest hundredth of a gram as to what the real, true, or accurate mass is for comparison. So compare your double pan balance masses to the masses you calculate using the techniques in part 2 and part 3 to get the unknown values.